All right. So today I am going to put some of the stuff that we've seen already together and show you a very, very nice result, a very famous result um, called the five color theorem. Okay, so this is what I'm going to show you today. The so-called five color theorem. So let me give you a little bit of background and then we'll jump into the very, very cute little proof. It's a very short proof, but it uses a lot of the stuff that we've developed up to this point. Okay, so background. At, at some point in the 19th century, and I've mentioned this, I should have looked up the exact dates. I don't know, but you can look it up. Somebody asked, is it possible to color all maps that we make with only four colors such that countries that have a common border get different colors, right? So coloring maps are four colors enough? Okay. Now, the answer actually took more than 100 years to figure out. So the answer was yes. It was proved by Apple and Haken in 1976. Answer yes. And so this was first proved by Apple and Haken in 1976. But this proof has an interesting status in the mathematical world in that it uses, there's a big chunk of the proof which is brute force computing. So essentially the proof breaks down the problem and reduces it to a certain number of essential configurations. And if you can color those configurations, you are okay. But the number of configurations is immense. Um, so they had to check it by computer. So this is not very satisfying for mathematicians. So people have tried to people have tried to find a purely argumentative mathematical proof. I don't know, that's not the right word, but with no computing or very little computing, it has been simplified, but still there is no known proof which doesn't use some computing component. Okay, still open today to find a non-computer proof. And that would be very nice, right? Because I mean, in a sense, if we have to do a lot of brute force computing, it means that we don't have a very elegant proof. Is there such a proof? Nobody knows, okay? But this is not what I'm going to show you, obviously. And by the way, the non-computing part of that proof is not easy. So it's not just brute strength computing, obviously. But what I'm going to show you is the five color theorem. So this says that four colors are sufficient, and I'm going to show something a bit weaker, is that five colors are sufficient. This was first proved in 1879. Okay, so five colors suffice. This goes back to 1879 by someone called Kempe. And this proof also has an interesting story behind, because Kempe thought he had a proof of the four color theorem, but there was a mistake in it. But you can rescue the five color theorem from Kempe's proof. Okay, so thought he had a proof for 4 colors, but there was a mistake. And it's a very natural mistake. And actually, when I was a much younger man, I made the same mistake. I was looking at the 5-color proof, and I thought, oh, but no, but wait, we can do this. But no, it doesn't work. I probably made the same mistake that campaign, and everybody does this mistake at some point. So okay, so I'm going to show you Kempe's argument, and but let's set up this whole thing. So what's the connection? What are these maps? What's the coloring? So let's set it up. So the first observation, and I'm not going to do this. I'm not going to do this very formally, but at least you'll see the connection. So let's say we have a map of countries, right? And we want to color the countries such that if they share a border, it means they have a different color. They get different colors, right? So if you have, let's say this is your map like that. So you should get, oh yeah, yellow is a good choice. Everybody can see yellow. So let's say this is blue. This could be blue. And we could have green here. And we could have green here. And magenta here, because magenta is a nice color. And maybe pink here, right? That's, yeah, you see, you see the idea. Okay, so okay, so what does this have to do with graphs? Well, here's the connection. Okay, so by the way, some of you right now are thinking, oh, but wait, some countries have disconnected parts and maybe they meet. Yes, there are all sorts of little tricky things that we have to deal with. And obviously, if we're considering connected countries here, and so there are all sorts of tricky little things that we have to take away to make this work. That's fine. That's okay. But here's the connection to graphs, and it's very simple. Okay, so I want to color the countries, and they must get different colors when they have a common border, not just a point, right? So here's how you can see this. I'm going to see every country as a vertex like this, and I'm going to put an edge between two of these vertices if the countries have a shared border, right? So this would be like that. This here. Do I have everything? I think yes. Okay, so countries are the vertices, and edges will be countries with common border. Does that make sense?
Yeah.
Yeah.
Yep.
Okay. So you see now that hopefully it is clear because we're being very informal. So clearly the graph that we're going to get is planar. Okay, the graph we obtain, and I don't want to go into a discussion of all the details of this because it's not the interesting part. Graph we obtain is planar. Okay, And again, I put clearly in quotes because there's a lot of details that we're just shoving under the rug here, but we're not really interested in this. So now here is the statement. Yeah, I should refresh your memory about proper colorings, right? A proper coloring. I've mentioned this when I did the introduction. I said I took some pieces from 10.8, which was this section here. So the proper coloring of a graph. What is that? It's an assignment of colors to the vertices. And you'll see this is exactly what we want, such that if vertices are adjacent, they get different colors, such that if X and Y are adjacent, they get different colors, which is precisely what we want here in our associated graph. Okay. So what I'll call a K coloring is a coloring using K colors. Obviously, if you try to use, you can always use a large number of colors, you can always do it. But if you reduce the number of colors, it might become impossible to do it, right? So a K coloring, proper coloring, but I'll drop the word proper. So proper coloring using K colors. Okay. Okay, so here's the theorem. Here is what I want to prove. This is the 5-color theorem. Keep in mind that this is actually true for 4 colors. So there's a stronger result that exists, but I can't show you the proof. So the 5-color theorem, every planar graph admits a 5-coloring. So you can have a zillion vertices. If the graph is planar, you can color the vertices with only 5 colors, and such that adjacent vertices get different colors. Okay, so this is the theorem that I would like to prove. Okay. So let's at least just do one little picture. I'm just making this up here, so I hope I don't make my life too complicated, but here's a planar graph, right? And rather than use colors, we usually use numbers because eventually it gets less confusing. So let's see if I can do this with 5 colors. If I can do it with less, I should be able to do it with 4, right? So let's see, I'll give this color here 1. Okay, maybe I can use 2 here. I'll have to use 3 here. I'll have to use, let's say, 3 here. This will be forced to 4, right? It's adjacent to 1, 2, 3. I can use 2 here. Maybe it'd be better to use 3, actually. Sorry. Oh, great. Let's say I use 3 here, 2 here, and 4 here. That's okay, right? So this is actually a 4 coloring, right? Okay. So again, you can always do it with 4, but I'm going to prove it. You can always do it with 5, okay? Because 4 is much harder. Okay, so let's see. Here's the proof. It's not very long. It's going to take me about 15 minutes to do it, but to explain it slowly, okay? Okay, first observation. Yeah, let's write that. So first observation, we can assume our graphs are connected, right? Because if you have different pieces, if you can color each different piece using 5 colors, then it means you can color the whole thing using those 5 colors because there are no edges between the pieces. So there's absolutely no conflict whatsoever, right? So if I have a piece here, right, and I have another piece here, right? If I can color each piece using 1, 2, 3, 4, 5, then I can color the whole thing. Hopefully, is this good for everybody? Yes. I've lost a few windows here. Let's see. Ah, this is better. Okay, good. And let's, I've got no chats. All right. Okay, so this should be obvious, right? Okay, so without any problem, I can just consider graphs which are connected, because if a graph is not connected, I just color the separate pieces and I'm done. Okay. Um, so now what I'm going to do, so I'm assuming my graphs are planar and connected, and I want to show that I can 5 color any such graph. So the proof, okay, there are 2 ways of doing it. It's induction, okay? But there are 2 ways to think about it. The simplest way to think about it is by contradiction, but by induction. Okay, here we go. This is a very, very standard. I meant to send you a link to, there was a new article this week in Quantum magazine about a new result in graph theory. Which is a proof of the Erdős-Haynel conjecture for C5 free graphs. But I realized that it would take me like at least a half hour just to state the theorem, and so I didn't bother. But the proof is indeed exactly of the same form as this. So it's proof by contradiction by induction. So you suppose that that there is a bad graph, right? You suppose that there is a planar connected graph which is a bad guy, and by induction there must be a smallest such bad guy, and then you show that there's a contradiction. Okay, so that's the strategy. Okay, so strategy. I mean, by the way, the connected thing, maybe I shouldn't have assumed this. It makes no difference. But if at any point I'm assuming something is connected, you see that you don't lose anything. Okay, so here's the strategy. Suppose for a contradiction, there exists a bad guy. In other words, there exists a planar graph that cannot be 5 colored. Okay, so we're going to suppose that there is such a beast. By induction, right? So what does what is the principle of induction I'm using? I'm using the well-ordering principle. The well-ordering principle, recall what it says, that if you have a set of positive integers which is non-empty, there is a smallest element. Okay, so it's actually the well-ordering principle that I'm using. So if you look at all the potential bad guys, look at the number of vertices that they have, right? So if there is a bad guy, it has, let's say, 572 vertices. You take the smallest possible number of vertices for such a bad guy. So there must be one by the well-ordering principle. So there exists a smallest bad guy. In other words, we have G planar, not 5 colorable, but every planar graph with fewer vertices is 5 colorable. Is everybody okay with this?
Yep.
Right? So if there is a bad guy, there must be a smallest one by the well-ordering principle. If you look at the set of number of vertices of bad guys, it's non-empty, so there's a smallest value. So that means that there is a bad guy for that number of vertices, and there are none with fewer vertices. Okay, this is a really classic trick in discrete math in general, where you take a smallest counterexample and you play with that. Okay, so recall the following lemma that we saw last week. And we saw that as a consequence of Euler's formula, that every planar graph has a vertex of degree at most 5, right? Every planar graph has a vertex of degree at most 5. And yes, this 5 is related to the 5 coloring thing, clearly, okay? Okay, so our bad guy, which is not 5 colorable, has a vertex of degree at most 5. Now I'm going to make the key observation for the rest of the proof. The whole architecture of the proof depends on the following observation. So I had my first, yeah, the connectedness thing, I don't think I need it, but okay. So I have a vertex of degree at most 5. Let's say X has degree at most 5 in our bad guy G. So maybe it looks something. I'm drawing 5 here, but it could be less, right? And so you look at, so this is G here like that, okay? What happens if I remove X and the edges incident to X? Okay, so you remove X and the edges incident to X. Hey boy. Okay, you get a new graph, G prime. What can you say about G prime? It's planar, right? G is planar. If I remove stuff, I get something which is planar. It has less vertices. Hence, it is, by induction, it is
What
5 colorable. Yes. Okay, so G prime is planar and has fewer vertices than G. Hence, it is 5 colorable. Okay, so I remove X, I get a new graph, and I know that there is a 5 coloring of this graph. So you look at it, and your job as a mathematician, doing induction, is you say, aha, if I can take this coloring with one vertex missing, I put back X. If I can find the right color for X, I win, right? I'll get my contradiction because I'm not supposed to be able to color G. Okay, so let me just illustrate what I'm trying to say, but that's the whole general idea. That's what we're going to try to be doing at every step. We're going to try to take colorings of this smaller graph and tweak them, mess around with them so that we can jump up to a big coloring for the bigger graph G. Okay, so here's here's an example. Let's say this is X. Let's just suppose that it was degree 4. Okay, what the hell? So suppose that we had the colors 1, 2, 3, and 5. So suppose neighbors of X got colors 1, 2, 3, 5 in a coloring of G prime. What do you want to do with X?
I guess we give it color 4.
You give it color 4. Exactly, right? So now you had this 5 coloring of the whole thing except X. X is adjacent to 1, 2, 3, and 5. So you give it color 4. And now you've got a 5 coloring of the whole graph G, a contradiction, which is exactly what we want, right? It looks, I know it looks weird because you say, oh, I'm finding a 5 coloring, which is what I want, but no, but think about it. You can think of, if you can think of the whole thing positively if you want, but it's, you really need the contradiction somehow. And that's how it works. So give X color 4 and you get a 5 coloring of G, which is a contradiction, and we win, right? Okay. So we're not supposed to be able to 5 color G is the smallest counterexample. Okay. We're going to show that it doesn't exist, that this presumed object G, we're going to show it cannot exist. Okay. Okay, but I just gave you a little example. What about if we had 3 neighbors? They get colors 1, 4, and 3. What happens now? What could I do? I'm being very silly here, but just to make sure you get it. I can
You can give it colors 2 or 5.
Yeah, I have a lot of room to play. Yeah, so X colored 2 or 5 win again. Okay, so now let's try to see all the winning cases, right? X has 5. Okay, here's the last one just to make sure. So let's say X is like that and it has, okay, hopefully you see that if X has less than 5 neighbors, we win, right? So otherwise it must have 5 neighbors. It can have more, which we know X has at most 5 neighbors. Let's say it has this. Let's just choose different colors this time. Let's say this. Okay, so X has 5 neighbors, and in the coloring of G prime, they get colors 1, 2, 1, 4, 5. Then you see X colored by the remaining color, which is 3. We win again. Okay, so for sure, we win in all cases if X has less or fewer, than 5 neighbors, or the 5 neighbors get fewer than 5 colors, we win. So we can assume that X has exactly 5 neighbors, and they get 5 different colors in a coloring of G prime. Otherwise, we can extend the 5 coloring to G. Is that okay for everybody?
Yeah.
Yeah, okay. So this vertex has 5 neighbors, and I know that if I remove X, I can 5 color the whole thing, and the 5 neighbors will get 5 different colors, because if not, I can always extend the coloring, and I'm done. Okay. All right. So the situation looks something like this. It doesn't matter what I call these colors, right? But this is the situation. So I have a 5 coloring of the whole graph except X. And you see I'm stuck at X because the neighbors they got 5 different colors. So I'm stuck. Okay. So our goal now is to make an analysis of this coloring of the remainder of the graph to see if maybe we can tweak it to change things so that we could maybe recolor in a correct way to get rid of one of these 5 colors around X. Okay. And that's the really cute part of the proof. Okay. So let's consider the following subgraph. Let's call it H of G prime induced by vertices. This is just a little bit tricky. Okay, I'm going to try to draw something to help you see it, but this is the only really tricky part of the whole thing. So consider the subgraph H of G prime induced by vertices colored 1 and 3. Okay, you'll see why I chose colors 1 and 3 in just a sec. Okay, so what is this? So this is a subgraph of G prime, and its vertices are all colored 1 and 3. So, okay, good. Suppose that in this graph, okay, I'll have to give names. So let's give names to these vertices. Let's call this U. Let's call this V. So suppose, and this is really Kempe's super trick. He was a happy guy when he figured that one out. Yes, actually he thought he had the 4 colors, but oh well. So suppose that U and V are in different connected components I'm going to draw something you'll see of H. Okay, so what does that mean? So I have all these vertices colored 1 and 3, and I suppose that U and V are not in the same component of this subgraph. So I can't, what does it mean is I can't reach V from U using vertices colored by 1 and 3. Okay, so I'm gonna show you a little example so you see what's so let's draw this like that. This is a planar graph. So there are vertices at all the intersections here. And I'm going to give colors 1, 5, 2, 5, 4, 5, 1, 3, 1, 2, 4, 2. Oops. 3, 1, 3, 1, 5, 4, 1, 3. Okay. So suppose this is G prime. I've lost someone. Suppose this is G prime, and I'm going to look at the subgraph induced by the vertices colored by 1 and 3. So they are here, right? That's one part, and the other part is here. Okay, so you see that these graphs are, this graph is disconnected. There are two parts. Okay. Here's the key idea. Suppose, damn. Okay, let me try something. Sorry. I had 1 here, eh? 1, 3, 1, 3, 1, 3. Okay, I'm good. All right.
I think you had 1 at the top left. Because if not, you have
Oh yeah,
two,
yeah,
three
yeah.
that are
That's right.
connected.
Yeah, that's wrong. Yes, thank you, thank you. Yes, otherwise it's not a good coloring. Okay, so these are the two different pieces. Okay, so I'm going to change this coloring, but it's still going to be a valid coloring. Okay, so this is the whole trick. So look at this piece here with ones and trees. Yes, trees. Threes. Okay, exchange the colors 1 and 3. Okay, hopefully you see that if you do this, you still get a proper coloring because it's not going to affect anything that, so if it's connected to 2s and 4s and 5s, whether it's 1 or 3 makes no difference, right? So exchange in one component the colors 1 and 3. So I'll use a different color. Like that. Okay. So is everybody okay? So you will obtain a proper coloring still. Is everybody, does everybody agree with this?
Yeah.
Nothing can go wrong, right? Because between 1 and 3, I'm good because I just flipped them, and connected to everything else, I'm good too because the others colors are 2, 4, and 5, so I'm not going to create anything bad. Okay. Now you're going to say, so what? Well, so what? Let's go back to our graph here. Okay, so I had U here and V here. Okay, so we said suppose that U and V, if you see it, you're smiling. Suppose that U and V are in different connected components of this 1,3 induced subgraph. So flip the colors, let's say in the component of U. Do you see what happens? The good thing.
And then you have a 3, U becomes 3.
Yes. And then we've reduced the colors around X, so we can now use 1 for X and we win. Yes. Okay, so if U and V are in different not in different, but in different connected components of H, switch colors 1 and 3 in the component of U only. We get a new proper 5 coloring of G prime, but this time, here's what we get. So by switching the colors, now I'm going to switch the color on U to 3, but still keep the color at V at 3 because they're in different components, so I can switch only in one. And so we win again. Right, color X with 1. Okay. So if that happens, we win again. So now we have to consider the case where U and V are in the same component. Okay, so now we assume U and V are in the same component of H. So what does that mean? It means that in H, there is a path from U to V. This path is vertices colored by 1 and 3. So here's the situation. Yeah. No. Okay, so somewhere in the graph, there is a path that looks like that. Like this. And these are colored 1 and 3. This exists. Okay. These things, which are also used in a more sophisticated way in the 4-color theorem proof, are called Kempe chains. Okay, so I can go from U to V in H, which is induced by the vertices colored by 1 and 3. Okay, all right. Now, I made the argument for 1 and 3. For any pair of colors, it's exactly the same argument, right? So now consider 2 and 4. Okay, so by the same argument, so if 2 and 4, by the same argument, consider the subgraph induced by vertices, man, this is long, colored 2 and 4, right? So if I look at 2 and 4, okay, if they are not connected in this subgraph, then I could flip the colors, let's say at vertex colored 2, and I win again. So they must be connected by a path colored 2 and 4. So there exists a path connecting the vertices, let's call them W and Y, by vertices colored 2 and 4. Okay, so I don't, yes, I still have it, good. So I have this situation. Something like that. This must exist. Okay. Oh, I lost somebody else. Okay, so I've got this situation and I've got this situation. Does anybody see? We're done. Okay, there's like one last line of argument. Basically.
Is it that we cannot have both? Because if we have both, then it's not a planar graph because they would intersect. Or
yeah, exactly. So I have a planar graph. That's the key thing. And if you look at these two paths, they will have to intersect somewhere, right? By the choice of, right? You see 2 is I mean, the picture is misleading. When I said there's a path going from U to V, right? I know that it will have to encircle at least one vertex, right? So I just chose arbitrarily that it is 2. Then I chose 2 and some vertex not encircled by this path, right? So So now I have these two paths which have to meet somewhere, but they can't for two reasons. Clearly, they have no vertices in common because one path, they're all colored 1 and 3, and the other path, they're colored 2 and 4. So there are no vertices in common. So this means that they would have to cross at an edge, which is forbidden because we have a planar graph, right? We're looking at a planar representation of this graph, obviously. So that's the final contradiction. This is not possible. Yes. Okay. So notice these two paths cannot intersect, right? So they have no vertices in common, which would be the only way they could actually meet. And G planar, so no edge crossings. So that's the final contradiction. It's not possible. Okay, so just to recap. Hello. Okay, so let's recap this. So I take a smallest possible bad guy, meaning that if I remove any vertex, I can 5-color what remains. Okay. There is a vertex of degree. Notice that we had to work earlier to find this vertex of degree at most 5. We had to use Euler's formula and blah, blah, blah. There was, I mean, we had to work. And yeah, we can erase the connected thing. It's not, I mean, I'm not using it. I should, yeah. So let's just, we don't really need this. Okay, so now I have this vertex of degree at most 5. I look at the coloring of the remaining smaller graph. If I get fewer than 5 colors on its neighbors, I can extend the coloring and I get my contradiction. Okay, so it means it has 5 neighbors. And what I do is I consider pairs of colors, right? And if they're not connected in the subgraph induced by those colors, then I can flip the colors in one component, just like I did in my little example here. And so then I can pump up my coloring. So it means that there is a connection. And once I have the connection for these two and then these two, and any pair will work, right? So you just choose the pairs so that you encircle at least one color and you choose another color outside the encircling, and then you get your contradiction. So that's the proof. Okay, so hopefully that was okay for you. And I'm done with the new material. I was thinking of doing the classification of platonic solids. If anybody's interested, I'll just let me know, and I will point you to last year's video. I haven't done this this year at any time, but if you want, I don't remember how good I did it, but you can just, but it won't be on the test for sure. Okay, this is the end of the new material, of the material of me too. I'm just, oh God. There's like a rumor. I mean, there's some talk that next semester would also be online, and I can't even imagine. Think of the first year students right now. Can you imagine if in September it's online? So they'd have to, they would have ended their high school online from March to June, then everything after that on is just insane. It's just crazy. Anyway. Okay. That's it. Philip, you had questions. So if you want,
Yes, absolutely.
yes,
Yes.
go ahead.
Okay, let me just pull back out what I was talking about. I was thinking about. So, okay, the question was on chapter 6, section 1, number 45. Yeah, number 45. So, chapter 6, number 45. Yeah.
Yep.
So the question goes as follows: that you need to place 6 people on a table, and that